So before we put everything together for linear programming, we're going to go over a few vocabulary terms. First off, linear programming itself. This whole idea in math is a way to maximize and minimize a linear objective function. So when it comes to maximizing and minimizing, this is especially important with businesses who try to maximize their profit given different constraints that they might have on supplies, hours of labor, and things like that. So they want to maximize their profit. The objective function, now this is the linear equation that we are trying to maximize. Often, if you think back to the business idea, this will have to do with profit because we want to maximize how much profit we can make. There's also other contexts for objective functions as well. Now, constraints, these are the inequalities that represent the boundaries of a function. And so the constraints are the restrictions that whatever the context problem is, might have on, say, resources and things like that. So for a business, like we said, you might have a limited number of supplies, you might have limited hours to work, and so those cause constraints. So we graph all of these constraints and we shade them because they're inequalities on a graph. And where all of the constraint graphs overlap, that is the section where we can find solutions. We saw before that when the shadings overlap, any points that would be within both shadings are solution points. And so that brings us to the next point, the feasible region. So this is the solution area shaded when all constraints are graphed. So it's the overlap of all of the constraints. Sometimes you have 2, 3, 4, however many. And you're looking for where they all overlap each other. Now, this can occur in two different ways. The first one is a bounded region, a definite shape. So, there's lots of different shapes that could come in. It can come in a quadrilateral, a triangle, a trapezoid, who knows? But a bounded shape it has sides, right? It has all sides, and then the most shaded region would be in between these points. And so this type of a region always has a maximum or minimum. We can maximize or minimize that function. But, and when that is true, then we have a uniqueness about that, which is the corner point principle. So what the corner point principle states is that if you have a feasible region that is bounded as a shape like this one is, then the max and min points will always occur at the vertices of this shape. So if you remember back to geometry, the vertices are the points on any shape. And so one of those points will be the max and one will always be the min. Of course, there are some feasible regions that are unbounded that continue on forever and ever. And those ones, they don't have a maximum or min because they continue on forever and ever. So let's put it all together here in part 4. Step 1 is we are going to graph the inequalities listed. So the first one we have, x is greater than or equal to 0. We'll start by graphing the line x equals 0. So that is a vertical line at x equals 0. Basically, it is the y-axis. And then we're looking for x's that are greater than or equal to 0. So we will shade greater than this line. That's going to be everything here. So that's pretty much just the first quadrant. I'm going to use a larger one for this. So we're going to just shade all in here. Okay, and now the next one says y is greater than or equal to 0. So I'm going to plot the line at y equals 0, which will be basically the x-axis right here. It's a horizontal line. And then we will shade above, which is kind of what we've already shaded with the orange I could also just kind of shade it like that, but I don't want to make it too messy. So just know it's basically the same region. We've shaded above that line. These two constraints, they're often kind of like the understood constraints, because when we deal with linear programming, often our problems, the context that we're dealing with, they cannot have negative numbers. So we're often always restricted to the first quadrant. So those two you will see quite often sometimes just as a given, because we know that we need positive values. The next one we have is x plus 3y is less than or equal to 15. The first thing I need to do before I'm ready to graph this is get it into slope-intercept form. So I'm going to take this, I'm going to replace that inequality with an equal sign. And I'm going to go ahead and solve for y. So I'll subtract over x. I get 3y equals negative x plus 15. Divide by 3. Remember that we need to divide every term by 3. And I get y equals negative 1/3 x plus 5. And now once I have that, I'm ready to bring back over the inequality. So it's not going to be y equals anymore. It's going to be y is less than or equal to negative 1/3. So there is the equation for this next one. I'm going to go ahead and plot it, starting with the y-intercept at y equals 5, and then using the slope, which is negative 1/3. So that's down 1 over 3, plot a point, down 1 over 3, down 1 over 3. And I really recommend for linear programming that you take the slope the entire way, because we want to be able to find the corner points very accurately when we put all of this together. So I'm going to go ahead and then draw the line. And then we will shade this graph. Now this one says y is less than or equal to the line, and so we will shade less than this green line. Now we've got one more here, and that's the 4x plus y is less than or equal to 16. So I'm going to go ahead and solve this one. Now, just so you know, if you forget to bring that inequality over, you don't have to replace it with an equal sign. You can leave it as is. It's not going to give you much trouble either way. So we've got y is less than or equal to negative 4x plus 16, and that one is good to go. So we're going to go ahead and plot that. We have the y-intercept at 16 and then a slope of negative 4. Remember that for slope it's rise over run, and if you have a whole number you can think of it as being over an understood 1. So we're going to rise down 4 and move over 1, and I say down 4 because it's negative. So 1, 2, 3, 4 over 1, 1, 2, 3, 4 over 1, 1, 2, 3, 4 over 1. See how that's intersecting there? That's awesome. 1, 2, 3, 4 over 1, because that's going to give us a really accurate corner point for the corner principle. So I'm going to go ahead and finish that and do some shading. For this one, we're shading less than or equal to the line. So we will shade below this blue line here. And we have now shaded all of the inequalities. So take a look, see if you can find what we would consider the feasible region. Today, for this problem, the feasible region is this region in here. This region that I'm currently outlining in black is where all the shading overlaps. You can tell that the color there is the mixture of the orange, blue, and green all together. So this is our shaded region, our feasible region. And that means that any point in this region can be a solution to these inequalities. But next what we want to do is we want to identify the vertices or the corner points. So I have one down here at 0, 0. The next one over here is at x is 4, y is 0. Then we've got up here at 0, 5, the y-intercept. And then we've got this point right here where those two lines had intersected, and that's at 3, 4. All right, now that we have the corner points, we are going to evaluate them in the objective function, which was given to us in the problem, in order to find the maximum and the minimum. So starting with 0, 0, that's going to be c equals 3 times x, which is 0, plus 2 times y, which is 0, and that'll get us a final answer of 0. I have a feeling this will be the minimum, but we will plug it into everything just to be sure. So now let's do 4, 0. C equals 3 times x, which is 4, plus 2 times y, which is 0, and we get 12. All right, let's do 0, 5. C equals 3 times x, which is 0, plus 2 times y, which is 5. We get 10. And then the last corner point at 3, 4, C equals 3 times x, which is 3, plus 2 times y, which is 4. And we get, let's see, 9 plus 8 is 17. So now we've been able to identify that the ordered pair 0, 0, this will be our minimum. And the ordered pair 3, 4, this will give us our maximum. Now, for this first example, we didn't have any context. We just kind of were graphing to see how they go together. But let's look at a problem where we have some context and we can actually minimize or maximize whatever that context is. So here we go. Example 2. A store owner wants to limit the weekly payroll to $960. Employees working regular hours receive $4 per hour, and employees working overtime receive $6 per hour. On the average, the store makes $18 for each regular hour of employee work and $32 on each overtime hour. If overtime hours are restricted to at most 2/3 of regular hours, how should the owner schedule working hours to maximize profit? Okay, so in this case, we don't have any of the constraints listed for us yet, any of those equations. We need to actually write them. So we're going to start first by defining the two variables that we are comparing in this problem. And what I noticed, we're talking about the weekly payroll at a job where employees work both regular hours and overtime hours. So those are going to be our two variables. We'll say that x can be the regular hours and y can be overtime. And now we're going to go ahead and write our constraints. So the constraints, these are things that are limiting the store owner. For example, in the first line, it says he wants to limit the weekly payroll to $960. So there's a limit, but we need to relate this to however much we're actually paying each type of hour, which comes in the next sentence, that regular hours receive $4 and overtime hours receive $6. So we're going to put this together in an equation. So we're going to take 4, which is for regular hours. We'll write 4 times x. This represents $4 for every regular hour, plus 6 times y. This represents $6 for every overtime hour. And when I add them, I get the total amount that needs to be paid for the hours worked. And we want to limit that to $960. So we'll say that this is less than or equal to 960. That's our limit. Let's see, as the problem goes on, we also see another restriction. Overtime is restricted to at most 2/3 of the regular hours. Overtime cannot go over 2/3 of the regular hours. So let's write this as a constraint. So we're starting with overtime hours, that's y, can be at most, so it can be no more than. This is going to be less than or equal to 2/3 of regular hours. So 2/3 times the amount of regular hours is x. Okay, so we have determined all the constraints from the problem, but also remember that there are some of those understood constraints, and that is that the number of regular hours cannot be negative, and the number of overtime hours cannot be negative. So we need to remember that the number of hours worked must be positive. All right, so we can then go on and write the objective function now. You could always graph it first. But the objective function, this is what we're trying to maximize or minimize. So how should the owner schedule working hours to maximize profit? So what that tells me is that profit is what we want our objective function to be. So looking back in the equation, what information do we have about profit? Well, we see that on average, the store makes $18 for each regular hour. So that means we make 18 for every X, and it makes $32 on each overtime hour. So that's plus 32Y. There's the objective function that we want to maximize. All right, we're going to go ahead and work on graphing this now. I'll start with, sorry everyone. I will start with this first equation here, and I do need to kind of make some more space here because I'm going to have to solve it and get it in slope-intercept form. So we have 4x plus 6y is less than or equal to 960. I'm going to start by subtracting 4x from both sides. I'm working on solving for y. So I get 6y is less than or equal to negative 4x plus 960. And then I'll divide every term by 6. So I get y is less than or equal to negative 2/3 x plus 960 divided by 6 is 160. All right, so now I'm ready to graph this one. We're going to start, we need a y-intercept of 160. So notice that our graph is not labeled yet because we know that we needed to figure out how high the y-axis needs to go before we can actually graph it. So maybe we could try to go up by 20s. Let's see if 20s work. 20, 40, 60, 80, 100, 120, 140, 160, 180. Okay, so that's how high we need. We need up to 160. So I'm going to go ahead and plot that y-intercept. And then if you want to be able to do your slope very easily, I always recommend the same scale for both the x and y axis. Otherwise, you're going to have to scale your slope differently, which is a little bit more challenging to do. So I'm just going to go ahead and do that. And now we'll use our slope, which is negative 2/3. So now I can just go down 2 over 3, down 2 over 3, down 2 over 3, and down 2 over 3. So we're going to have to go 220. Oh, that's up at 240. All right. And there's our first line. And then we're going to go ahead and shade that. We say y is less than or equal to the line. So we're going to shade below. All right. The next one that we have is the y less than or equal to negative 2/3 x. That one's actually already ready for us to graph. It has a y-intercept of 0, so I'll plot that point here, and then a slope of positive 2/3. So I'll go up 2 over 3, up 2 over 3, up 2 over 3, and continue that pattern until we're off the graph here. And then for this equation, it is y is less than or equal to the equation. So we're going to shade below the line. All right. And then the last part here is going to be those two understood constraints, and that is that x is greater than or equal to 0 and y is greater than or equal to 0. And remember before, this was just the x-axis and the y-axis, so we're really just shading in the first quadrant here. And I can do them both kind of at the same time. That'll kind of save your shading. If you put too many colors, sometimes it gets a little too muddy. So I'm just going to shade up here in the first quadrant. And we can start to see what would be considered our feasible region. And that feasible region here, where all of the shadings overlap, is this lovely triangle right here. So that would be in here. So the vertices for our feasible region, we've got that first one at 0, 0. We have another one at 120, 80. And the last one is at 240, 0. Now we're going to plug these into the objective function to find the best solution. We want to maximize the owner's profit. Starting with the first one of 0, 0, well, if we don't work any hours at all of any kind, we're obviously going to make a profit of $0. So that is not the maximum. The next one, we have 120 regular hours and 80 overtime hours. So I'm going to use my calculator for this one. 18 times 120 plus 32 times 80, I get $4,720. And then the last one, for working only 240 regular hours and no overtime hours, we would get 18 times 240 is $4,320. So now we can see that we can maximize the store owner's profit by recommending 120 regular hours and 80 overtime hours. All right, let's try one more example here. Mine is cut off in example 3, so give me 1 second. All right, I've pulled the correct notes up on my phone, so we can go over this. I'll read it from here. Your notes should be fine, though. So question 3 says, piñatas are made to sell at a craft fair. It takes 2 hours to make a mini piñata and 4 hours to make a regular-sized piñata. The owner of the craft booth will make a profit of $14 for each mini piñata sold and $22 for each regular-sized piñata. If the craft booth owner has no more than 40 hours available to make piñatas and wants to have at least 16 piñatas to sell, how many of each size should be made to maximize the profit? All right, step 1, define the variables. The crafter wants to make 2 types of piñatas, and that is the mini piñata, so I'll say that's X, and the regular sized piñatas, I'll say that's Y. All right, next we're going to determine the constraints. So the constraints here, the first one in the problem is that he has no more than 40 hours available to work. And it tells us that it takes him 2 hours to make a mini piñata. So 2 hours for every X, plus it takes 4 hours to make a regular piñata, so 4Y. And he has no more than 40 hours, so this total must be less than or equal to 40. And then the next constraint, we know he wants to have at least 16 piñatas total. So that's X, the mini, and Y together. So X plus Y needs to be at least 16. This is going to be greater than or equal to 16. Those are the only two constraints from the problem, but remember we also have those reasonable constraints that we cannot make a negative number of piñatas. So that's going to restrict us to that first quadrant here. Now the objective function, we're trying to maximize his profit again. So we're going to have a profit function. And we know that he makes $14 for each mini piñata, so 14x, plus $22 for each regular sized piñata, so 22y. And now we're ready to graph. All right, we're going to start by finding the slope-intercept form for our first equation here. 2x plus 4y is less than or equal to 40. I'll start by subtracting over 2x. Then we will divide by 4. Remember to divide each term. And I get y is less than or equal to negative 1/2 x plus 10. We also have a second equation here that we need to solve, and that's the x plus y is greater than or equal to 16. For this one, I'll subtract over x, and I get y is greater than or equal to negative x plus 16. So first thing I need to do before I can graph these is go ahead and scale my axes. And the highest y-intercept we have here is 16. So I think I can possibly go up by 1. So let's see. 1, 2, 3, 4, 5, 6, 7, 8. I think I was wrong. Just 1 too short. All right, so we will go up by 2's then instead. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Remember, do the same along the bottom too. This is going to help you when you're graphing and you have to use slope to graph. And I'm going to go ahead and graph the first one. Y is less than or equal to negative 1/2 x plus 10. So we're going to start at the y-intercept of 10 and use the slope of negative 1/2. So down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2, and down 1 over 2. And we have our first constraint graphed, and let's go ahead and shade for that one. Y is less than or equal to the equation, and so we're going to shade below the line here. Okay, the next one is y is greater than or equal to negative x plus 16. So we're going to start at 16 for the y-intercept, and then our slope is negative 1. So that's down 1 over 1, down 1 over 1, down 1 over 1, and we're going to keep going with this slope all the way down here. And then for this equation, it's y is greater than the line. So we're going to shade actually above this one here. That's everything above. All right. And then the last ones we have are the reasonable constraints. So that means that we have to have positive numbers. So here's the y equals 0. Here is x equals 0. And we are shading in the first quadrant, which is everything around here. Oh, it's hard to see that color. Let me try one more color. Use the pink. And we have, for this problem, a very tiny feasible region way down here from this point. And if it was just a little bit neater, they'd really intersect. But we've got a lovely little triangle right here. That is our feasible region. So the vertices that we have are 16, 0, 20, 0, and the one here is at 12.4. So let's plug these in and find which of these points will maximize the crafter's profit. P equals 14 times 16 plus 22 times 0. Now this would represent making 16 mini piñatas and no regular size piñatas. And if he did that, he would make $224. The next one, this is 14 times 20 plus 22 times 0. So this would be making 20 mini piñatas and no regular size piñatas. He'd make $280. And then finally, if he made 12 mini piñatas and 4 regular piñatas, he would make $256. So, in order to maximize his profit, the crafter would actually want to make 20 mini piñatas. That's not how you spell mini. There you go. 20 mini piñatas for a max profit of $280.